I'm Mohammed Sadasan from the Petroleum Engineering Department, and in this term, as part of Geology 201, I wrote a paper entitled Properties and Characteristics of Silicate Minerals. I chose this topic because of the importance of silicate minerals. Silicate minerals constitute about 92% of the Earth's continental crust. The main aim of writing the paper was to educate normal people with little knowledge of geology about this very important mineral group. As you know, silicates fall into two categories: dark silicates and light silicates. Dark silicates are the ones that are darker in color, and light silicates are the ones that are lighter in color. So we'll start by talking about dark silicates. The silicates we're talking about are pyroxene, olivine, amphibole, biotite, and garnet. This is what the mineral pyroxene basically looks like. The general formula, as you can see over here, is XYSiO2O6. Now, this part is found in all pyroxenes. What is different in different pyroxenes is the elements in the X and Y sites. In the X site, we usually have elements like calcium, magnesium, iron 2, and sodium. In the Y side, however, we have stuff like chromium, manganese, iron 3, etc. This mineral is found in most igneous and metamorphic rocks and has a very simple single chain structure. As you guys know, our Earth consists of three layers: the mantle, the core, and the crust. Pyroxene minerals form one of the main ingredients of the upper mantle. Now let's move to olivine. This is what it looks like. As you can see over here, the mineral has an olive green color. And that is how it gets its name of olivine. The general formula is over here at the top. Now, in different olivines, the composition or the percentage of SiO4 is constant. What is different in different olivines is the percentage of magnesium and iron. So the olivines that are rich in magnesium form rocks like gabbro and basalt. Olivine rich in iron is quite rare, but we do find it in some places, and such olivines are responsible for forming rocks like granites and rhyolites. Okay, now let's move to amphibole. This is the mineral amphibole. Amphiboles are very similar to pyroxenes, but there are some important differences, however. For example, amphiboles consist of a double chain structure. Pyroxenes, as I told you, consist of a single chain structure. And there are also some chemical groups that we have in amphiboles. These chemical groups are not found in pyroxenes. I'll write them down for you on the board. Chemical groups like the hydroxyl group, or H group, and halogens like fluorine, chlorine, etc., the elements of the 7th group of the periodic table. These elements are absent in pyroxenes. Amphibole is found in most igneous and metamorphic rocks, and there are two types of amphiboles: acidic amphiboles and alkali amphiboles. Acidic amphiboles are the ones that are rich in elements like sodium, potassium, elements of the 1st group of the periodic table. Acidic amphiboles are the ones that are rich in halogens, like fluorine, chlorine, etc. And now let's move to biotite. It is also known as black mica or dark mica because of its color. It has a very simple single sheet structure. When biotite exists in large pieces, it resembles books or textbooks. So that is why huge lumps of biotite are known as books. In fact, the biggest piece was found about a couple of years ago in Norway, and it is 7 meters squared in area. Now we come to garnet, a very expensive gemstone. This is the chemical formula of garnet. The different types of garnets have similar physical properties, but what is different in them is the chemical properties. And that difference in chemical properties arises due to the presence of different elements in the X and Y sides. Now, usually in the Y side we have aluminum, and in the X side we have calcium. We have many other elements in the X and Y sides, but those are rare types of garnet, so we will not be talking about them over here. That concludes our talk about dark silicates. Now let's move to the light silicates: feldspar, quartz, and muscovite mica. These are the three types of light silicates that we'll be talking about over here today. This is the mineral feldspar. In the beginning of the talk, I told you that silicates make up about 92% of the continental crust. The minerals that we've just talked about make up a very small portion of the 92%. The most abundant mineral in our crust is feldspar, makes up about 60%. This mineral forms from both intrusive and extrusive igneous rocks. Intrusive are the ones that are formed inside the earth, and extrusive are the ones that are formed on the surface. There are three types of feldspars that I'll be talking about today. The first one is K-spar, K from potassium, the chemical symbol of potassium. Then we've got albite and anortite. The solid solution of albite and K-spar is known as alkali feldspar. Solid solution means a solid mixture. The solid solution of albite and anortite is known as plagioclase feldspar. This one is plagioclase feldspar. Let's move to quartz. It has the simplest chemical formula of SiO2, and after feldspar, it is the most abundant mineral in the Earth's crust. Different types of quartz are categorized due to their different colors. There are three types that we'll be talking about. The first one is rock crystal. It is transparent. This one is rock crystal. Then we've got smoky quartz and milky quartz. Smoky quartz is opaque, you cannot see through it, and milky quartz is milky in color, basically. Now most of you, I'm sure, have seen quartz as a separate mineral in the laboratory, not in nature. So I got a small sample from the rust formation for you guys, and you can see the mineral quartz in it. If you guys want to see it, you can pass this around. I got this from the lower rust formation a couple of days